on basic concepts on in HDL, as well as also we will try to discuss, if given enough time, gate level modeling. Okay. So to start, let me share my screen. I understand you have classes. What time is your classes for today?
Hello na, Pastor.
1? Sige. 1 pa di ay. Sige. Katong klase ninyo, Sir Darwin, sunod sa ato, magklase mo, dili? Online? Dili ra? Sige. May feedback. Pasig dili. Okay. So let's try to have a short discussion on the basic concepts in HDL. So what we were doing in the laboratory. Okay, thank you. In the past weeks. So again, we had recalled on HDL. In the last meeting, we had defined what is HDL, what are the benefits of having HDL. And also, we differentiated Verilog and VHDL. So for now, we will try to discuss the basics of Verilog and then the different types of descriptions, as well as also gate level modeling. So objectives for this morning is to read simple Verilog HDL description. Next is to be able to write simple Verilog HDL description, although you have already wrote HDL descriptions. And then we will also try to understand katong hardware view, the drawings that I made sa katong dito sa board. Those are the hardware view. So in Verilog, take note sa Verilog, the notations are the following. So Verilog is case sensitive, meaning ang katong commands pareha sa other programmings, case sensitive siya sa. Verilog is based on C programming. Verilog also has comments. So you have single line and multi-line comments similar to other programming language. And then when you would want to declare variables as inputs or outputs, you can define multiple variables, inputs or outputs via comma. Sa mubutang ratag comma, that is the least element separator. And then also Verilog utilizes a terminator, kanang semicolon. So in Verilog, the binary values for constants and variables would be the following. Would be 0 or 1, X or Z, a high impedance circuit. Might be nga during your simulation in GTK Wave, you might see values nga ubusa, which is 0. And then there are values nga high, which would be 1. And those others might have experienced katong naay puwa. Sa katong naay pula nga mga values. Sa katong naay puwa nga linya taas kaayo. Others also had experienced kanang Z. Sa katong Z, katong yellow. So might be that those values are unknown because you were not able to identify the sources of those values, or might be the variable that you're using was not declared. Mato nga ni unknown siya. Going into constants, so if you're utilizing constants, so constants can be represented in decimal, in binary, and in hex. So if you're going to utilize binary, the formatting for a binary value, if it is a 1-bit value, you would say 1, single quote, and then B, meaning that is a binary value, and this one is the 1-bit value nga imong gi-assign niya, which is a 1-bit value nga 1. So kung mayroon ka 1, single quote, B niya 0, meaning that is equivalent to a 1-bit binary value nga 0. If you have an 8-bit value, so maingon ka 8, single quote, B, that's an 8-bit binary value, niya assign it into this one, this 8-bit value kana siya. 1, 2, 3, 4, 5, 6, 7, 8. Sa So that would be, mingon ra kay nga ni, 8-bit, tapos ang katong X nga values, pwede sad IMP or unknown nga values. Sa, and then a 4-bit value is this one, 4-bit value. For a hex value, you can also assign or convert it into hex, such as this notation, which is converted as A as 10 and 9 as 1001. And then in Verilog, the identifiers or the variables can be single value, which is known as a scalar, or an array of values known as vector. And ang array din sa Verilog is known as a vector. A single bit value is a scalar. This one can be, this 8-bit value could be represented as a vector. So examples of vector, like we would say, vector select from 0 to 2, meaning you have created an array of select whose variables are select 0, select 1, and select 2. And then you have F, which is also a vector from 0 to 5. That would tell us that there are 6 elements, so from 0 up to 5. F. Then you also have this one, an accumulator, ACCs, accumulator 31 down to 0. The good thing with Verilog is that unlike the ordinary array in the programming in C or in Java, wherein the indexes or the index would start at 0, here in Verilog, you can assign the arrangement. Pwede ikaw magbuot sa arrangement. Pwede from high to low or from low to high. Pareha ani. From 0 to 5, kani saya ha, pwede po from 31 to 0. Unsay pasabot ani from 0 to 5. Meaning kung nakay F sa, kung nakay F, nga unom kabuk ang values, this is F0, F1, F2, F3, F4, and F5. Ingana ang arrangement. However, kung nakay ACC or accumulator, 31 down to 0, so mani ang imong ACC, dot na lang taha until maabot as kinalasan. So this one would be 31, kani siya ang 30, 29, until you reach 0. Nasabtan ang kalainan niya. So again, ingana ang vector sa Verilog. Pwede ikaw magbuot sa arrangement. Pwede ang index from the leftmost will start at 0, going to 5, or pwede po start from the highest, going down to the lowest. Mao nay kalainan sa array sa Verilog. Gitawag na natog vector sa with the vectors in other programming or array in other programming. Also take note sa, there are some times that this kani-kani bitawng iyang index would not start at 0. There are some codes that you might see bang wala lagi siya nagsugod sa 0, 1 lagi siya nagsugod. Pwede sana siya makabuot ka unsay range sa imong index. That's also a good thing in the vectors in Verilog, which is quite unique compared to the other vectors in other programming. Copy? So I do hope nakuha sa. There's also a sum from 15 down to 0. Okay, next. So Verilog keywords and constructs. So keywords are lowercase. The module is the fundamental building block for Verilog design. So every time that we create a new module, we say module. So module and then the module name as well as also the ports. So kung naatay module nga buhaton, that contains now a block. And then the ports would consist of the inputs and also the outputs. Pwede daghan, pwede rapod usa. So again, it contains the input and the output every time that we create a module. In general, we create modules as well as also we create the simulators and we create the test bench. So every module, we would need to create a simulator that will produce values for our module. And also we create a test bench so that we can connect the two. We can connect the two modules, the simulator and the module. We can connect them by means of instantiating. Sa kinaubsan nga part sa atong code, mato ang test bench. Also, the module is closed or ended via the end module command. Okay? So take note the module cannot be nested. Dili pwede na module niya sudlan pud nimo og lain nga module sa sulod. The modules should end first before you create another module. Pwede sa imong usa ka program daghan jud kayo module sulod. Kay ingana ang construct sa Verilog, wala siya construct to reuse the codes that were previously created. Kanang modules nimo pwede nimo ilaray din na tanan. In the declaration of the module, you say module name, and then the module ports, of which these ports, after creating the module, you need to assign whether these ports are input or output ports, pasulod or pagawas nga data. So input declaration, so you can say input and then the name of the input. Sa input A, B, C in, you can also create an input of a vector values. Input 15 down to 0, A, B, and data. It tells us that A is a 16-bit vector from 15 down to 0. B is also a vector which is 15 down to 0, and data is also a vector 15 down to 0. Okay? Vector na siya, tag 16 bits ang A, B, o ang data. Kung ingani lang, ordinary lang nga variable, sa single bit value lang na siya. Then you have also output declaration. So when you declare an output, you say output and then the name of the variable. So also shown in here is a declaration of a scalar and a declaration of vector values. So output and then the range of the vector and then the name of the variables. So it tells us the accumulator is an 8-bit value which is 7 down to 0. Register input is an 8-bit value also, and the data output is also an 8-bit value. 7 down to 0. And then we have already used the basic logic gates, so we call as the primitive gates. This is included in the next topic, which is the gate level modeling. So the primitive gates that are available includes the buffer, buff, the NOT gate, AND, OR, NAND, NOR, XOR, and XNOR. The syntax for the gates are the following. The first variable is the output. The next variables, succeeding variables, are the inputs. So you can create primitive gates with more than 2 inputs. So as long as you put comma, excluding the buff and the NOT. Kaya ang buff ug NOT, usara jud input ana nila. All the rest, you can have multiple inputs. Okay? So example of which, mingon ta AND A1, meaning nag-create ta og AND gate, sa AND gate, which is named as A1, whose input values are A and B, and then the output value is F. This one is an OR gate, U1, and then W is the output. Inputs are A, B, and C. You can put a comma di ay dinhisa. Pwede ka magbutang og comma para magbutang na pud kaglain nga OR gate. No need nga mag-declare ka og OR na pud lain. Pwede ra imo isumpay ingana. That's the good thing of having Verilog primitive gates. Okay? Which we have already used. So other operators aside from the primitive gates includes the bitwise operator. So which includes the NOT, any bitwise NOT, bitwise AND, bitwise OR, XOR, and the XNOR. But for now, we will not be utilizing these operators because we'll start with the gate level modeling. Kani nga mga operators atong panggamiton. When we go into the next modeling, we will use these operators. And then there are also the other operators such as the arithmetic operators, the plus, minus, and then the logical operators sa equal, not equal. Also the relational operators. Logical, sorry, is the not and or. And then for the relational operators is equal to, not equal to, greater than or less than. Greater than or equal, and then less than or equal. There is also a special type of operator known as the concatenation operator and the replication operator, which is only available in Verilog. Concatenation meaning iyang isumpay ang mga values. So in concatenating, you would try to use the open, close, curly brace, and then the variables that you would want to concatenate. Mga variable nga imong gusto isumpay ang value. So example kani, reg in which is a 6 down to 0 and a serial in. Meaning, ang 7 bits sa register input ug ang serial in na 1 bit, iyang i-sumpay, iyang i-concatenate. Thus, it becomes an 8-bit value. Again, that is an 8-bit value. This one, on the other hand, the ISA, this one is what we call as the replication. This is the replication operator. Again, this is the replication. This one is the concatenation. So, ang concatenation, iyang isumpay. Ang replication, iyang i-replicate. Example, natay 8 dere niya, 1 bit down, 1 bit 0. So, meaning magbuhat si ana og 8 kabuok bits na tanan 0. Manay pasabot ani niya. Magbuhat siya 8-bit value. Ingani, 8-bit value nga puros 0. Manay pasabot ana niya kanang replication nga operator. So unlike sa concatenation nga iyang isumpay, sa replication iyang i-multiply n number of times. Kani man ang n sa n number of times. Sige, so we have already created this one. The simple circuit sa next would be the stimulus generator. Katong mag-produce og input stimulus sa so the behavioral constructs such as initial and always can be used to generate stimuli. Initial statement is similar to a program. Each line is sequentially evaluated and only run once. Kanang nasa initial begin sa padagano na sa imong program, kausara. By default, the statements are evaluated concurrently. To separate the statements in time, we use the delay. So example, kanang katong gibuhat nga simulator, which we also call as the stimulus generator. Mao na siya atong gibuhat. So natay initial, begin, also we end. So these statements are executed concurrently but will be sequentially run when we use the delay operator. Kaning delay operator ang maka-sequential niya. And then also the test bench. Notice that when we try to write test bench, we try to instantiate the modules that were created on the top portion. So we would say simple circuit SC1, simple circuit simulator SCS1. So these are now the objects that will appear in your GTK wave. Sa kung nakabantay mo. Kaning mga variables dire nga inyong gigamit during instantiation will be the variables nga mo appear in the GTK wave ninyo. Sige. This one was your practice. So let's now proceed to the next topic. Okay, so that's more likely of a review raman sa. So let's now proceed to the next one. After the basic concepts in gate level in HDL. So I'll be activating, by the way, an activity for today. So we will try to discuss basic concepts. This was the discussion for today, basic concepts. So we'll now proceed to the gate level modeling. Okay. So going over now to the next topic, which is the gate level modeling. So take note that in Verilog, there are many different types of modeling. So we have the structural, or commonly known as the gate level modeling. So after this topic, we will try to discuss concepts in Verilog using gate level modeling. And then we will try to design commonly used combinational logic circuits and then implement combinational logic circuits using gate level modeling. So mag-implement tayo using gate level. So since it is called as gate level, it is noted that we will be utilizing the basic gates or the primitive gates in Verilog. So recall that in logic circuits, a circuit can be represented, a combinational logic circuit can be represented in three possible ways. Its Boolean equation, its Boolean equation, kani siya, the Boolean equation. Another possible representation of the circuit could be the truth table, and another one could be via a schematic diagram or a logic circuit implementation. So for which, these three possible ways for which we can model the circuit is also defined in Verilog to be described in different models. So we have the first type of modeling, we have the gate level modeling. This use instantiations of predefined and user-defined primitive gates. So, unsaon na nato magpagamit ang gate level modeling? Dapat naatay schematic diagram. Pareha atong gibuhat nato sa nakita na nato nga na ang diagram. So once na ang diagram, di na ta maka-create og gate level modeling. And then we also have the data flow modeling using continuous assignment statements with keyword assign. And also behavioral modeling using procedural statements with the keyword always. So kana ato nang makitaan in the next chapters sa kanang data flow modeling ug behavioral modeling. Specifically, inigabot nato sa sequential logic circuit, manood na taog gate level modeling. For combinational logic circuits, we can use gate level and data flow modeling. Okay? Sige. So for gate level modeling, in this type of representation, a circuit is specified by its logic gates and their interconnection. Gate level modeling provides a textual description of the schematic diagram. The Verilog HDL includes 12 basic gates as predefined primitives. 4 of these primitive gates are of the three-state type. The other 8 are the same as the ones. So, unsa man na sila? And or not, sa XOR, XNOR, sa pa, NAND, NOR, buffer, napakunoy 3-state gates nga available. Sa 12 di kuno na sila. So AND, NAND, NOR, OR, XOR, XNOR, NOT, and the buffer. There are also additional 3-state gates which are special modification of the buffer and the NOT. 3-state gate. 3-state because the outputs could be of 3 possible values. 0 or low, 1 or high, or Z, which is a high impedance. High impedance values are undeterminate state values. So the first of the 4 3-state gates is the buff if 1. The buff if 1 gate behaves like a normal buffer if control is equal to 1. Meaning, kung ang control nimo kay 1, unsay value sa imong input, mao po'y value sa imong output. Kung 0 na siya, 0 po na. Kung 1 ni siya, 1 po na siya. That is the buff if. The buff if 1, that is the buff if 1. The buff if 0, take note guys kung 0 ni siya kay high impedance. Kung 0 ang control, high impedance Z na siya. Second is the buff if zero. The buff if zero gate behaves in similar fashion except that the high impedance state occurs when the control is 1. So si buff if zero, balipod siya. Kung 0 ang control, unsay value sa imong input, mao puy value sa output. So kung 0 ni diri, 0 pud ni. Kung 1 ni siya diri, 1 pud na ang output. Pero kung ang imong control kay 1, high impedance ang output. That is the case for the buff if zero. And then we have the not if. So the not if gates operates in a similar manner except that the output is the complement of the input when the gate is not in a high impedance state. So example, in the not if 1, if control in here is 1 and your input is 0, not man na siya, dapat ma-invert. May mong 1. Kung ang imong input kay 1, may mo pong 0 ang output. Pero kung ang imong control kay 0, may mo siyang high impedance. And then we also have the not if. In the not if control is equal to 0, na may invert diri sa kani. Anawa, na invert din na. So if control is equal to 0, kung 0 ang control, high impedance. But if control is 1, kung 0 ang input, ang output 1. Okay? Kung 1, may mong 0. That is the not if. Okay? So in gate level modeling, when the gates are simulated, the simulator assigns one value to each of the output of each gate at any instant. In addition to the two logic gates of 0 and 1, there are two other values, the unknown and the high impedance. The unknown value is denoted by X and high impedance is denoted by Z. The unknown value is assigned during simulation when the logic value of the signal is ambiguous. For instance, if it cannot be determined when its value is 0 or 1. A high impedance occurs at the output of three-state gates that are not enabled or if a wire is inadvertently left unconnected. Walay connection. That's a high impedance. When a primitive gate is listed in a module, we say that it is instantiated in the module. In general, component instantiations are statements that reference lower-level components in the design, essentially creating unique copies of those components in the higher-level module. So in this type of representation, a circuit is specified by its logic gates and interconnection. So it is quite easier to do gate-level modeling if you already have the schematic diagram or the logic diagram of the circuit. Gate-level modeling provides a textual description of the schematic diagram. So in this modeling, dapat naanatay diagram ng logic gates, naanatay schematic diagram. Okay? So let's try to look into the exercise that we did last time in the half-adder circuit. So notice that this was your half-adder circuit or you can implement it like this. Pwede yung nga na ang atong implementation. Okay? So let's try to create, manaman mo ani, so let's try to create the next example, which is the full adder circuit. So recalling that a full adder is a combinational logic circuit that performs addition between 3 bits. Ingani to siya ang solution nato. Di na nato manwalon og solve ha, man na matag-solve na last time in the logic circuit na subject. So if we try to see, let's open our Notepad++. Okay. Okay. So if we try to see the solution of our full adder, nga na itong dagway sa atong full adder wherein you have the carry as equivalent to C is equal to X times Y plus X times Z Basta na-solve na nato sa plus y times z. On the other hand, you also have the sum. So for the sum, medyo taas-taas tong sum. But you can also simplify this one. You can also simplify this one by means of saying sum is equivalent to, sa tong atong sum is equivalent to, sa shortcut notation, ana, XOR man to. Sa XOR man to. That is sum is equivalent to x, XOR y, XOR z. Okay. So we now try to create the code for our full adders. So again, sum is equivalent to x, XOR y, XOR z. So you can say sum. Ba ni diri? Okay, wala. Is equivalent to x, XOR y, XOR z. Nga nasa? So we will now try to implement our full adder. So in implementing our full adder, so let's try to go into our Verilog. Okay. Medyo dagko ra itong pagamyan ha. Para medyo klaro-klaro siya. Okay. So let's try to create our module. We say full adder. Wala pa ta kabuhat sa half adder sa. Talantong agion ng half adder kadiyot. Atong buhaton ng half adder kadiyot. Okay. So let's try to create the first one, which is the half adder. This was our activity last Thursday sa. So we say module half adder. So in the half adder, sa itong half adder, Mana half adder. So in the half adder, we have inputs x and y, and then the outputs as s and c, the sum and the carry. You can also say gagmay lang sa s nga gamay, c nga gamay. Then end module. We say this one also as half adder dot b. Okay. So in this one, we will try to set the x and y as inputs, and then also the c and s as output. Now we take note that we will try to instantiate using the gate level. So mingon ta cs XOR, we can say G1. We name this one as G1. Then we name this one as G2, meaning gate 1 and gate 2. So we say XOR G1. So the output is S, the inputs are X and Y. And then also, we have an AND gate, we'll say G2, whose output is C and the inputs are X and Y. That now ends our half adder module. Then we will try to create the half adder simulator. So module half adder simulator. In the simulator, we will try to have only two outputs that will become the input to our half adder. And that would be the X and the Y inputs in the half adder. So we would say in module, and then we will try to declare output for X and Y. At the same time, we also declare register for X and Y. And then we use now the initial begin, and then we say dump file. So this is now half adder.bcd, and then dump vars. So, and then lastly, on the last line is the finish. Sorry, na dollar symbol. Dollar symbol. So begin, so napod tayo end. So kanang begin, kuyog niya ang end. Kaning module, kuyog niya ang end module. Kaning dump file, kuyog niya ang finish. So we now try to assign values to our X and Y. So we can say X is equal to 0, y equal to 0, and then we can say a delay of 2 or a delay of 3. So you just simply copy and paste. Then this is now 1, this is now 1, and this is now 1 and 1. Kumana siya ang upat ka values sa ato ang half-adder circuit. So we will now go into, after the simulator, we now go into the test bench. So we say module half-adder test bench. Okay, so for the test bench, wala ra siya ports. Kaya nga naman, naa siya sa sulod ang katong mga module na ito gibutang. And module. So we will try to instantiate the two modules, namely the half-adder and the half-adder simulator. So may nga half-adder HA1, and then the inputs X, Y. Take note sa sequencing sa SC. S and C. And then also, half-adder simulator, HAS1, X and Y, only 2 inputs. At the same time, we need to connect the modules, wires in here and the wires in here. So mingon ta, ang nag-connect din na is the wire, X and Y. Kanang duha ka wire ang nag-connect din na sa mo na siya. So that is now your half-adder test bench, your half-adder and your half-adder simulator. We say, then we'll try to use MD. So we now go into our drive D and the IR. We go into CD CPE P20 DIR. So this is now our code. The half-adder .V. So, okay. So we now try to say Iverilog -O, and then the output file name HA. That's for the half-adder 1. We say half-adder .V. So if there are no errors, then you can proceed with BVP HA1. Once a dump file is created, you can now say GTK wave half-adder .BCD. Okay. So this is now our output for our half-adder. So in our half-adder, we have the X, the Y, the carry, and the sum. So we click on this one, click at 0. So notice that the values 0 and 0 for X and Y, 0 plus 0, sum of 0, carry of 0. And then there's a change in here at the 3-second interval in which Y becomes 1. So 0 plus 1 is 1 and a carry of 0. Mga to, inig-check na ako dito sa laboratory. Sa mingon ko, click ka na yung mga nausab nga values. Okay, tanawon man nina ako, kani dering dapita akong tanawon. 0 plus 1 is 1, and then 1 plus 0 is 1, and then 1 plus 1 is sum 0 carry 1. So mo ni siya. There is a. Mana akong gitanaw, ining mag-check ko sa inyong exercise. Okay. So we now proceed into the full adder. So again, going back into our full adder. So we now create the code for the full adder. So creating the code for full adder. We save this one as full adder.v. So we create the module full adder. And then for the full adder, there are now 3 inputs, X, Y, and Z. So we say X, Y, Z. Still, we have the sum and the carry. Mga ba itong sunod sa ito ang ganiya? Sum and carry. Okay? We say end module, and then we define the inputs as X, Y, and Z. The output as S and Z, S and C. And then we just simply try to create the circuit in here. So example for our C, sa atong C, tanawa atong C, natay X, natay Y, natay X, natay Z, natay Y, natay Z. So we take note that these internal connections in here, we have still no connection. So we create a wire. So mingon ta wire 0, this is our wire 0, this is our wire 1, and this is our wire 2. So you have options on creating the variables for the wire. You can either, first option, you can use scalar values sa tagsa-tagsaon nimo W0, W1, W2. Another option is by means of utilizing vector. So pwede maingani ka sa pwede mingon ta din ha wire W1, W2, sa to W0, W1, W2. So that's the first option. Second option is by means of utilizing a vector. Pwede ka mag-ingani nga vector. Vector 0 to 2 or 2 down to 0. So we call this one as W. So meaning na kay W index 0, W index 1, and W index 2. For this case, our W will be kanisa kani ang atong W. So first we will try to assign W1. So we try to assign gate numbers. So this is gate number 1, gate number 2, gate number 3, and this is gate number 4. Okay? So that is now an AND gate and G1. Take note sa and G1, and then you can now say kinsa man na siya W index 0. Kinsay inputs niya X ug C, Y. Can have another gate G2. Sa kinsa man na si G2, si G2 kani. Ang iyang output si W1, W index 1. The inputs are X and Z. So X and Z. Another AND gate G3. The output is W index 2. W index 2. The inputs are Y and Z. Sa Kapas ra ha. Sunod, we also have gate number 4. Gate number 4 is an OR gate. So mingon ta OR G4 whose output is equivalent to the carry. So kanang carry sa so mingon ta diri carry C, the inputs are W index 0, W index 1, and W index 2. That is our OR gate for the carry output. Also, you have your S. So for your S, you can use this one or you can use the simplified version kanisiya sa ana siya. So we're in S. Sa S is utilizing an XOR gate. We'll call that as G5. Kay G4 man isa, so we'll call this one as G5. Output is S. The inputs are X, Y, and Z. That is now our full adder. After having our full adder, we now try to create our simulator. So we will say module full adder simulator. For our simulator, we have three outputs. So we have X, Y, and Z. So we say output X, Y, and Z, wire X, Y, and Z. And then initial, begin, end. And then we say dollar symbol, dump file. And name this one as full adder.
Excuse me, sir. Dili na
Yes.
register, sir.
Registered, not wire. And then, thank you. Dump bars, and then finish. And then we assign now values for X, Y, and Z. So we say X equals to 0, Y equals to 0, and Z is equal to 0. A delay of 3 or 2. Just copy. Okay. So this is now 1, 1. This is now 1 and 1. Then we copy also this. Then we change this 1 to 1, 1, 1, 1. That now completes the truth table. Katong truth table ng mga values. 8 values. That completes the truth table values. So after our simulator, we now try to create our test bench. Module, full adder, test bench, and module. So we'll just try to instantiate the two. So we say full adder FA1, X, Y, Z, S, and C, and then full adder simulator FAS1, X, Y, and Z. Sorry, X, Y, and 0, wala SC. And then we create wire for X, Y, and Z. These wires we connect in our circuit. So that is now the code for our full adder. So we save and then we try to compile. So compiling, we would say iverilog -O. So we say FA1 full adder dot B. Then we say VVP FA1 and then we say DTK wave full adder at VCD. So this is now our full adder. So for the full adder, it has FA1 and FAS1. So we are concerned with FA1. Okay. So you now try to click on X, Y, and Z, the sum and the carry. Carry and the sum. Okay. So you can also check this one if this will match in your table. So looking into your table. So when the inputs are 0, kanasa, the carry is 0, the sum is 0. In here, when 001, the sum is 1, carry is 0. Yeah. Next one, 010, that is carry of 0, sum of 1, still correct. In here, 011, kana 011, sum is 0, carry is 1. Then you have 100, kanisa kani 100. That is sum of 1, carry of 0. Next one, 101, kani 101, carry of 1, sum of 0. Carry of 1, sum of 0. Kapas, nakita? Kita raha. Sunod. 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 Ani? 110. So 110 kani siya, sum of 0, carry of 1. Kani? Kani siya. And lastly, 111, sum of 1, carry of 1. Okay? So that is our full adder circuit output. That is the first possible implementation of the full adder. Okay? Second possible implementation of the full adder. Sa naputay katong laing implementation sa full adder. Katong mo gamit og duha ka half adder nga circuit. Sa this is HA1. So half adder 1. Kani half adder 2. So ang full adder, instead of i-add nato ang X plus Y plus Z diretso, ang buhaton nato X plus Y. So kani siya X plus Y, kani siya X plus Y. Nya ang output niya himuon nga i-plus na pud sa Z. Sa ingana ang dagway sa atong circuit. So we will also implement this one today. So we will name this one as full adder version 2. Okay? So I do hope nakahinumdum pa sa concept anang kuansa anang full adder nga implemented using two half adders. So ato sa ning sugdan sa dinhi. Ana. So let's create a new code. So we'll name this one as full adder version 2.p. Okay? So we say module full adder B2. Okay? So this still the same, X, Y, and Z, S, and C. So take note, this will utilize the concept of half adder. So in creating the full adder version 2, first we need to create the half adder circuit. So module half adder circuit in here. So again, in our half adder, we have X, Y, the sum, and the carry. Okay? So we will try to set the input values as X and Y. The outputs are the sum and the carry. So again, we will try to take note that so to, sum is equal to X or Y. So mingon ta ato X or G1, sum is equal to X or Y. And then carry is equal to AND gate and E2, which is carry is equal to X and Y. Mao ba na itong decode or bali? Mao lagi. Sa mao na. Or you can also copy and paste. Katong nahuman na itong half adder, kopyahan itong module, i-paste din na. Sa. And then we implement now the full adder using two half adder. So we say now input X, Y, and Z. The outputs are S and C. Sorry, sumpay mo ni. Output S and C. Take note that this is our HA1. So this is our half adder 1. So we will try to create an internal wire. So kaning wire sa kani na adder. We'll call this one as W0. Ya kaning wire na adder. We'll call this one as W1. Napabaylain nga wire, internal. Kani. We'll call this one as W2. Napabaylain, kanara. Kanara sa? Kanara. So that is now our code. So we have, instantiate the half adder which was created. Half adder HA1. Atong half adder nga naas taas atong gibuhat, atong gi-instantiate using the naming convention nga atong gipalo. HA1, ito man tayo na niya nga input X ug Y. So ningon ta, ang iyang inputs kay X ug Y, ang iyang output kay ang sum niya kanisa si W0. Wala pa ta nakabuhat og wire. Buhat ta tag wire na W. 2 down to 0. Tawag na to og W. Sa init na dere sa opisina. So this is now, the output now is W. Ang sum niya kay W0. Nakapas ang iyang carry kay W1. So W index 1. Apas ha? Apas? Sige. So now we now go into half adder 2. Kani siya, half adder 2. So ang iyang X kay ang W0. X man ni siya, di ba? Sa imong half adder, kani siya ang Y. Kani siya ang Y. So ang imong X gikan ni W0. So mingon ta half adder HA2, ang iyang X kay W index 0, ang iyang Y kay W index 1. Sa nakapas, ang iyang sum kay si S. Ang iyang sum kay si S na gyud. Sa Ay, sorry, dili. Si W1. Si Z di ay ang iyang Y. Ang iyang Y, gikan ni Z. Tara. Z. Si W0, gi-plus ni Z. Ang iyang output kay si Sam S, nya ang iyang carry kani si W2. W index 2. Kani. Kapas, guys. Kapas, ha? Masigwa kapas. Nangangangalan taan eh, wala kapas. Okay, sunod. Ano nga part? Ako ibalhin diri speakers, ha? Ano nga part? Mao man ni atong W2, nya mao na ang S. Okay na ang S, kaya nakuha naman ang value sa S. Pero ang value sa C, wala pa. So, ang pagkuha sa value sa C, magbuhat ta og laing nga gate. Naman tay gate 1, gate 2, butang ta og gate 3. So that is an OR gate 3 whose whose output would be C and inputs are W1 and W2. So W index 1 and W index 2. Nakaapas, guys? Amana na ang atong code sa full adder now. This version 2 utilizes two half-adder circuits in getting the value of our sum and carry. So after which, we will just try to create the test bench and the simulator. Full adder version 2 simulator. So for the simulator X, Y, and Z, actually, you can just copy and paste the simulator in here. Pwede rin siya kopyahon. Copy na lang na din, ha. Sa parehara na natog i-type, pas-pas pa ito i-copy. Wala man tayo usab sa input. Pero ang kaning BCD file niya, atong butangan of version 2. Full adder B2. Okay? Para makakita sa tanga, dito ma-overwrite-an ang unang file. And then also, we will create the test bench. Module full adder B2 test bench. And module, also you can copy and paste the same. Pero instead of full adder lang, natay full adder version 2. Full adder V2. So mingon ta FAB2. Then we have X, Y, Z, S, and Z. S and C. Then full adder V2 simulator, FAS V2, X, Y, Z, and then also create a wire that will connect the three wire X, Y, and Z. Ano na? Ano na siya? So karon atong padaganon, atong i-compile ni atong padaganon. So notice akong padaganon ang una nga DTQ wave katuning karon. Katuning ganiha, katuning first versions X, Y, Z, carry, and sum. So ako sanang i-minimize. Sorry. O din ang screenshot. Kaya ato nang i-compare sa ganiha, sa kaning bago. Atong gi-screenshot lang ay para atong i-compare dito. CLS and then Iberlog -O FA full adder B2 full adder B2.B and then VVP FAB2 and then also we say isa pa mana na sa GTK wave full adder B2.BCD. Okay, so let's check if the output is correct. So we have X, Y, Z, the sum, and the carry. Also take note, if you click this one, na ato din ang HAS1 ni Musa. HA1, nara. HA1 o HA2. Kita mo na HA1 na po HA2. Katong gibutang dito sa code. So if we try to compare the output Sa output sa atong diagram diri pareha ra ba sa atong GTK wave karon? Pareha ra? Pareha ra sa. Take note, this is a different implementation because we use a previously created half adder in our design for the full adder. This is what we call as from bottom to top sa gagmay nga components nga atong gigamit in the next design. Pero ang nakaparat niya kay we need to put it in the code again. We cannot reuse. Sa wala tay import or wala tay include or wala tay extends. Dire, i-code yun ni mo balik or i-copy ni mo balik. Any questions or clarifications? Nasabtan? Parehara output pero lahi og implementation. Sa dire nagamit man tag half adders sa atong version 2. Okay na? Nasabtan ra? Sige. So if that's the case, I guess I'll save this one. So there are still some other examples in here, but we will continue this one on our next meeting. So discard. So what I'll do is I'll be first okay. Try to delete the codes guys. Karaan yung mga codes. So I'll try to upload the new codes that we created today. So these are already codes that we have created in the past. So now I'll try to upload the codes that we have created for today. CPE 320, type, full adder. Okay. Nana din ha. Save changes. At the same time, let me try to create a sheet work for today. So there is in here a picture for which you can download and implement. So this is the picture of what you will be implementing for today. So let me try to change the settings. So this is activity number, this is actually number 3 na sa. This is number 1 in the online. Number 1 lang in the online. So that will be for today, February 11, until 8 in the evening. So kung napa mo yung mga lakaw, napalay mo yung mga lakaw sa, pwede mga alas 10 lang siguro. 10, so kana. Available today. Okay, so February 11. So what you will be submitting in here is the screenshot of your GTK wave as well as also the code in .v file. So duha ka book inyong i-upload ha, ang .v ug ang GTK wave nga screenshot. Okay. So let me check asa to si activity number 1. Let me try to enable. Show. Okay, so makita na nasa basic concepts. Okay, anong sheet work number 1. Sige. So any questions so far? Questions or clarifications? May pangutana? Walay pangutana?
No, sir.
Sige. Nana ba yung attendance ng atong LMS? Wala pa yung attendance di isa? Baka tanta ng attendance di. Attendance. Okay, so and then we'll create a session for today. So add session February 11, 8 until 9. Nangalan ako 9:50 na para maka-access pa mo. Every Saturday until May 31.